Hi, this is Marcus. I gave this talk at the 2021 IS4SI Summit. This video is on my YouTube channel where you can pause and repeat sections or download the video as needed. This talk on a theory of meaning extends Claude Shannon's 1948 concept of signal entropy. Okay, in considering a theory of meaning, one must first state what is information, so I start with a general view. When I say information, I point to the known cosmos, all of material reality with mixed forces and matter. This unbroken, self-evident universe has no interpretive needs or logical gaps. It shows a necessary unity long before the arrival of modern humans with fractured views of information. We often call this unified primal reality, nature. Next, nature brings sentient life. Sentience has agents giving meaning to reality, experienced as life and death. That sensed reality is individual and discrete, partial to each agent, with diverse niches where agents prove survival skills. But survival varies in each case, with many ways to live one's life. Those mixed views of survival incite subjective agent biases. Still, any and all survival strategies show biological and behavioral adaptation, with life-death as a central meaning. This interactive material reality with diverse referential agents I call an informatic system, and what fills that system I call information. Information is thus content to an informatic system context, within a vast continuous material reality with myriad niches. Such common sense views are often missing from information studies, but are key to framing deeper issues. Without a firm starting point, later analysis is often vague. Step 2 next shows a narrow scientific view of information. Here, Claude Shannon's 1948, A Mathematical Theory of Communication, is central, dividing the engineering problem of signal mechanics from the meaning innate to all messages. This logical split allows one to isolate logarithmic and statistical traits in all messages, which Shannon called entropy. Signal entropy is now the scientific standard in depicting information, a widely accepted view, but with clear gaps. For example, in 1949, Shannon and Weaver call signal entropy disappointing and bizarre, as it omits meaning and in equating two distinct types of entropy. But they also say these gaps can be closed with a practical theory of meaning, the goal of this talk. Toward a theory of meaning, in 1952, a semantic theory of information first appears, but wins little acceptance, as with all following efforts. Later, Shannon notes signal entropy's growing role, where many people gloss over clear gaps in the model. Today, 70-plus years later, a missing theory of meaning still plagues diverse researchers in many areas. Despite signal entropy's gaps, a theory of meaning seems likely, as suggested. One candidate is metadata, often called data about data. For example, the Standard Model of Particle Physics and Periodic Table are each metadata, holding material primitives in a specific order to mirror reality. Thus, metadata are better called knowledge about data or knowledge about reality. Beyond metadata, meta-meta views also exist. A meta-meta view uses logical primitives instead of material primitives for a base. Logical primitives are domain-neutral elements that allow one to frame a general vista, in contrast to domain-specific material primitives. One early meta-meta example is dialectic logic, born of a pre-Socratic era. Darwin's natural selection of diverse evolving species is also meta-meta. Lastly, Shannon's signal entropy is meta-meta, with logarithmic and statistical primitives depicting all messages. Next, in step 3, to better show signal entropy in relation to logical primitives and a theory meaning, I reduce signal entropy to its core elements. First, if we accept signal entropy as a valid concept, We must also accept Shannon's split logic of objective engineered elements as existing apart from semantic meaning. Ideally, a theory of meaning would join those two parts in one coherent role. Thus, I call this approach subject-object modeling, or SO modeling. Semantic roles show in many ways, depending on the context involved. So naming a semantic logical primitive is the key task here in framing a theory of meaning. Second, Shannon starts his study with a message selected at another point and sent across a channel. But for a priori analysis, unlike Shannon, we must first ask, what is it that even allows the message to exist? Messages start with agreed-upon objects, symbols, and sounds as base terms. For example, many writing systems and languages exist today. Each such group of agreed terms I call a set, and each marks another type of metadata for those sounds and symbols. Likewise, the standard model and periodic table each show settled terms in nature's messaging. Such normalized sets, whether man-made or natural, already show a meaningful difference, with regular features and being well ordered. As such, space-time order, at a most basic level, is a likely logical primitive in an eventual theory of meaning. This view of base meaningful roles collides with Shannon's claim that semantic issues are irrelevant to the engineering problem, as all messages plainly arise from meaningful sets. In fact, mathematics consists wholly of agreed sets of various terms, each noting a meaningful role. This is the same for Shannon's logarithmic and statistical roles. I herein refer to such meaningful data sets as set entropy. Next, specific groups of object terms frame each message. For example, numbers can have identical terms where different space-time roles alone invoke different values. But new object terms also incite new space-time relations to yield different messages and meaning. Joint subject-object operation makes S and O co-evolve in driving messages and meaning, which I call group entropy. Lastly, the scale of SO grouped terms also shifts messages and meaning, but at yet another level. Shifting SO scales mirror Shannon's notion of a scalable logarithmic base that is sometimes called statistical surprise. But they do little more than serially extend already named space-time traits. At this point in the analysis, we come to the same place where Shannon begins his level A entropic analysis, used to develop signal entropy. In summary, shown above is what affords a message prior to Shannon signal entropy. It starts with a base sense of meaning, detailing specific facets, instead of using a message selected at another point. Each of the three entropic levels invoke a different objectified space-time role, again, making space-time a likely logical primitive in a theory of meaning. This view of SO modeling shows a central dualist role, along with the three entropic levels, jointly creating a dualist-triune pattern. Lastly, eliminating any one of those dualist-triune roles defeats signal entropy, as one would expect in an a priori analysis. Higher-order semantic roles also reduce to essential space-time traits. But explaining such roles surpass this talk's a priori aim. Still, at this point it becomes possible to formally define information in these terms. As a final note, I invite you to read the companion paper, which is listed in the link below, and which covers more detail. I also leave you with a few more dualist-triune examples as a generalized view of broad reality. Thank you for your attention.